So this is Antonis Michalas. I'm an assistant professor at Tampere University and leading work package 2 of ASCLEPIOS. So this is a brief presentation for regarding the progress that we have made on WP2 till now. Right, so some logistics for the work package. So WP2 started on month 4, 1st of March, and it will end on month 21 at the end of August 2020. So the work package has 6 tasks and 4 deliverables. So if I had to somehow split out or categorize the main tasks and deliverables of the work package, I would say that we have 2 main categories. The first category is related to cryptography, and the second one is related to analytics. So on crypto stuff, we have 2 main tasks. T2.1, which is about symmetric searchable encryption and how we can also implement this kind of, computationally heavy schemes on constrained devices such as medical devices. And then task 2.2, which is how to utilize another modern encryption scheme, which is attribute-based encryption, in order to allow more granular access control on encrypted data. So both tasks, basically, they have there's a one-to-one mapping with tasks and deliverables. So T2.1 maps to deliverable 2.1, which is about symmetric searchable encryption, and T2.2 maps to deliverable 2.2, which is about attribute-based encryption and the generation of a protocol that will allow us to provide some access control on encrypted data. Now, for these 2 tasks and deliverables, we have 1 milestone, M2.1, which is due to month 15, and it's basically the design of secure and privacy-preserving searchable encryption scheme, as well as the design of a cryptographic cloud storage, basically based on attribute-based encryption and the combination of SSC. Now, on the other hand, on the other side, we have the analytics tasks that are split into 4 tasks and 2 deliverables. So the first 2 tasks, task 2.3 and 2.4, they map to 1 deliverable, which is the deliverable 2.3, which is about the GDPR compliant and privacy preserving analytics for healthcare providers, while the last 2 tasks, 2.5 and 2.6, they mainly focus on analytics at cross CSP level and data owners privacy analytics, and they map to deliverable 2.4, which is about data owners and personal health data privacy preserving analytics, which is due to month 21. Now, we have 2 milestones here, milestone 2.2, which is due to month 18, and milestone 2.3, which is due to month 21, which is at the end of the work package. Good, so let's start describing the work that has been done till now on this task. So first of all, we have the SSC, the symmetric searchable encryption scheme, which is basically our main mechanism for storing data from the client to the server, to the cloud. So we assume that we have a user here on the left side, Alice, and she wishes to store some of her medical data to a remote location, which is probably owned or operated by the hospital, and it's basically cloud server, right? So Alice generates a file locally, and she starts, adding some data in that file, for example, ASCLEPIOS security coronavirus, right? Then she generates locally a symmetric key, a secret key, basically, that will be later used to encrypt her file. Now, before she encrypts her file, what she needs to do is that she needs to run a program that will extract all the keywords from the file and will generate the hash of these keywords. Now, after she parses all of the data contained in that file, then she uses the key that she generated earlier in order to encrypt the file. Now, the encrypted version of the file, along with all the generated hashes of the data in the file, will be sent to Bob, to the CSP. Now, upon reception, Bob basically gets all this data and he stores the file in a storage resource like a hard drive, and all the hashes that received by Alice, that was sent by Alice, all the hashes are stored in a remote database. Now, then Alice, after she gets a confirmation from Bob that everything has been stored properly, she deletes her file, right? So keep in mind that at this point, basically, the initial file that contained Alice's data in plain text has been removed, so you cannot see it anywhere, right? So the only thing that you can see is an encrypted representation of Alice's data, right, with a key that is only known to Alice and no one else. So her actual data can be only found in an encrypted form, and Bob doesn't have access to the key that Alice used to generate this encrypted version of her file, so Bob can't say anything about the contents of the files. Good. So now the magic thing about searchable encryption is that Alice can start searching over her encrypted data without revealing anything to Bob. So let's assume that Alice wishes to search for all of her files that contain the word coronavirus. To do so, she will have to calculate the hash of the keyword coronavirus, the hash of the keyword that she wishes to search for, and send, I'm simplifying things here, right? So send this hash of keyword to Bob. Upon reception, Bob can search in his local database, find all the files that contain the hash of the keyword that Alice is searching for, and return back all the encrypted files to Alice. Now keep in mind that with the design that we have implemented and created for ASCLEPIOS, Bob cannot tell anything about the actual keyword that Alice is looking for. So Bob cannot know that Alice is looking for the all the files that contain the word coronavirus. Okay. However, he is able to find all these files. Now, Bob returns back to Alice the encrypted version of the file. Upon reception, Alice, that she's the only one who has access to her key. She uses her key to decrypt the file and therefore access all of her medical record, right, contained in that file. And that's how basically SSC works in a nutshell. So let's talk a bit about our work on AB, which is connected to task 2.2, and it's about storing and sharing our keys. So Alice basically has already, as we showed in the previous slide, has already stored her medical records on Bob's database and remote storage. Now, the good thing about cloud computing is that we can share our files, right? If we are not able to share our files, then basically we are losing one of the main properties of cloud computing, and therefore we don't really have cloud. Good. So let's see how this can happen. So Alice, she generates her local key, her personal symmetric key, and what she can do is that she can encrypt it by using what we call MPK, a master public key, and the policy. So the policy can be anything like you know, for example, who can access her key, basically, okay, who can access her files. For example, anyone who lives in Brussels and he's at least 28 years old or something like that, or he's female or male or whatever. So she uses these two pieces of information, a master public key that is known to everyone and a specific policy in order to encrypt her symmetric key. And this encrypted version of the key will be sent to Bob. Keep in mind that Bob cannot decrypt that key. So the only thing that he can do with that key is to store it in a local hard drive, right? So Bob gets that key, that encrypted version of Alice's key, and stores it in a local hard disk. Now, let's assume that we have another user, a doctor or a patient, whatever, that she wishes to access Alice's data, right? So that lady here, she has her own attribute-based encryption key. So each user that registers at ASCLEPIOS has its own attribute-based encryption key, which is a unique key based on attributes. So what she can try to do is she can contact Bob and say, please give me Alice's key. Now, upon reception, Bob, first of all, needs to verify that the request comes from a legitimate user, which means a registered user, and not a revoked user or a malicious user or something like that. And if everything goes well, then basically he returns back to the user the encrypted version of Alice's key. Upon reception, our friend here will use her unique and personal attribute-based encryption key and try to decrypt Alice's key. The decryption will only work if the attributes that contained on the key of that user satisfy the policy that is attached on Alice's key. So if this works, then basically our friend here, she will be able to recover Alice's key and therefore access her data. If not, then she will not have access to Alice's data. So for this, we created a proper protocol on how, and we described how this can properly work. Now, our achievements for these two tasks. So first of all, we created, we designed and implemented a forward and backward private SSE scheme, which means that every time that you search for a keyword, Bob cannot identify that a user is searching for the same keyword. Okay, so this is the notion of forward privacy. Or if you add a new file to the database, then Bob cannot know that two files contain the same keywords. Okay, now about the backward privacy, the notion says that basically that if you delete a file, okay, Bob doesn't know which keywords deleted and contained in that file. Now, apart from that, we provided support for the multi-client model, which means that most of the schemes basically till now they were only supporting single client models, which is really bad for cloud-based services, because if you imagine that SSC basically targets cloud-based services, if you are losing the multi-client option, then you don't really get advantage of the cloud functionality. Apart from that, we proved, we showed that our scheme has an optimal search and update cost, and therefore it's a really efficient SSE scheme. And also we formalized the cryptographic cloud storage with the use of attribute-based encryption and its combination with the SSE. And we also proved the security against certain malicious behaviors. Good, so then we move on to task 2.3, which is mainly about privacy preserving analytics, and I will mainly focus on our work that we did on functional encryption. So again, we have Bob, who has stored the files of all of our users, and then imagine that we have Alice. She generates a file with her medical records, like her age, her name, surname, address, etc. And then, for example, she says if she's positive or negative to coronavirus, right? For example, in that case, corona equals to 0, which means that she's negative, so she's not a carrier. Now, Alice, she has her own unique key that is used to encrypt this file, right? Good. Now, assume that we have another user with different unique data again. So age 34, but she's a corona carrier, so she has been infected. She has her own secret key to encrypt that file, and then we have another user and with his own data, his own key, and so on and so forth. So imagine that we have basically n different users with different data. Now, all this data will be sent to Bob and will be stored on Bob's side. Now, imagine that we have a doctor that he wants to run some kind of analytics on this encrypted data. So you know, that doctor, she doesn't have access to all these keys required to decrypt the data, and we don't want to give access to those keys. So what we will be doing is that we will run a functional encryption scheme that through which the doctor can ask Bob, give me the average, for example, age of all corona carriers in your database. And in a magical way, Bob, without getting access to the individual data, to the individual plaintext values, can calculate the average age of all coronavirus carriers stored in his database and return the number 50 to the doctor. So the doctor gets the result that she wants, but without getting access to the individual values, right? So basically we managed to create a scheme, a cryptographic scheme that allows real privacy preserving analytics. Now, our main achievements, we designed a novel, provable, secure functional encryption scheme. We support the multi-client model, which means multi-input functional encryption scheme. So our scheme can get input from several users and not only from a single user. It is efficient since it is solely based on symmetric encryption, and therefore it's really fast. And we designed its integration with ASCLEPIOS. Even though this hasn't been finished yet, we have designed it on paper. Now about task 2.4, so basically the main objectives were to identify analytics around the techniques used by healthcare providers to secure their infrastructures and the data and information owned or exchanged. We defined metrics and analysis processes to monitor encryption activities, measure security incidents, and identify emerging threats and trends, sort out patterns of abnormal and unsecure behavior, and finally to provide some insights to stakeholders in order to help them understand their systems regarding security, encryption, and access. Now, the key results from this work is that we performed a landscape review on cybersecurity threats and challenges for healthcare organizations and presented methodological and technical solutions towards establishing cybersecurity strategies. In addition to that, we examined data analytics and visualization techniques that can be leveraged in implementing targeted anomaly detection solutions in the field of healthcare. We identified healthcare providers' needs into monitoring data encryption, decryption, and access patterns. And finally, we implemented the cybersecurity encryption and access analytics component, which provides targeted insights to help healthcare providers gain a deeper understanding on their system and build threat preventive mechanisms. Now, then we move on to task 2.5, which is about personal health data descriptive analytics at cross CSP level. So imagine that we have multiple users that they generate their data and they're sending their data into a pool, let's say, through a multi-party computation protocol in order to calculate some statistics. Now, what is important here is that we are running an MPC protocol, a multi-party computation protocol, which means that all these users, they will somehow collaborate in a magical way, and even though their data is not encrypted, nothing is revealed at the end of the process, nothing is revealed about their individual values, right? So this protocol will basically calculate some results based on the medical data of each user, and only the result will be sent to the doctor. Therefore, we can basically run even complex, more complicated statistical operations than in the functional encryption example I gave earlier, and the doctor can run analytics without breaching the privacy of users. Now, our achievements, first of all, we managed to compute descriptive statistics on the combined data. We removed the need for centralized data collection. That's why, we use an MPC model, and it can be run in a distributed manner. So we achieved privacy-preserving distributed statistical computations, and we designed its integration with ASCLEPIOS and functional encryption. So we are now working on how to find the proper balance between the analytics that will be used by ASCLEPIOS through functional encryption, which means on encrypted data, and through MPC models, which is the unencrypted data. Good. And then we have the last task, which is task 2.6, data owners privacy analytics. So the idea here is that Alice, at some point, she wants to know how her data has been used. Therefore, she can send, let's say, imagine that she can trigger Bob by saying, hi Bob, can you please tell me how my data has been used? For example, since the beginning since I started using your service, for example. Then Bob, what he will do, he has stored a bunch of log files for certain functionality of Asclepios system, and he can find all the information that Alice is asking for, let's say, and return back to Alice, for example, the data or the type of the data of her data that has been used by Asclepios, when, by whom, and for what purpose. Right now, the important thing to mention here is that even though you might think that this is a simple problem to solve, having such a functionality when we are using such a secure and privacy preserving searchable encryption scheme, it was quite challenging because our SSE scheme doesn't allow the leakage of any information, right? So it wouldn't be possible to find to log this information at the SSE level. As a result, we came up with a way around it, and we just created log files on the application side, right, on the demonstrator side. So on the application, for example, we store some log files based on the functions that are going to implement it by the application, okay? And we don't log anything that is taking place in the SSE. Good, so beyond the state of the art, so first of all, we defined and served a set of analytics to show data owners how their data is being processed. We managed to create log files in a forward and backward private SSE system, which is and was quite challenging. We create a conceptual design of Asclepios privacy analytics module. And finally, we designed its integration with Asclepios, which is still a work that is going on, still in progress. So about our future plans, basically until the end of work package and until the end of work package 5, which is the integration, basically we are planning, first of all, to complete all of our implementations for all of the schemes and then functionality that we just described, and we have designed. But we are also working on extending some of the encryption schemes that we have created. For example, we plan to create extra functionality for our functional encryption scheme. In other words, basically we aim to create schemes that will support more complicated, more complex functions than just calculating the average or the sum of encrypted numbers. We are looking on how to improve even further the efficiency of our SSE scheme, and also we are looking on how to extend the functionality of our multi-party computational statistical approaches. That was it. Thank you very much.